Testing, can you hear me? Okay, this video is now public. So I'm going to be studying calculus. I'm going to study where I left off from last time. I studied Green's theorem last time, but my stream did not record properly. So I'm going to revise it this stream. Okay, let me change to full screen. Right, so last stream I studied about conservative vector fields. So from what I remember, um, okay, let me try to remember what I done last time. So let's say we have a vector valued function RT. RT is a vector value. So RT gives a vector. So and as t changes, the vector changes. So vector valued function, they define like a particular path. So if we have this curve defined by RT, and in this graph, there's also a vector field, capital F. Yeah, capital F. So vector field is like in every position of xy, they define a particular vector. They can be in any direction. So what we want is this thing over here from curve C, going through curve C. The F dot tangent, actually, yeah, ds. So tangent is like unit tangent vector. Tangent is like when you're going through RT. Tangent is like a unit tangent vector is the change in RT. The tangent is the change in RT and it's a unit vector. So we are dividing it by this. And S over here is the like a piece of the curve. So curve is cut into many pieces. If those pieces was infinitely small, that's ds. So this integral is basically saying, for each tiny piece, we multiply the vector field at that point with the tangent at that point, and we sum the multiplication for infinite points. So so for example, vector field at this point, let's say it's over here times the tangent. Then vector field at this point, let's say it's facing this direction times the tangent. This product for infinitely many points. So ds is like infinitely small. This is equal to, like, let's say RT, this over here. It goes in this direction. This is T is equal to A. It starts here. And then T is equal to B. It ends here. So we have A, B. So this is equal to F, the vector field at that position, times it by, you do a dot product with this dt. So this is how we calculate it. So this is a vector line integral. And then there is a conservative field. So conservative field is like, if you have F, which is a vector field. Actually, let's start it differently. Quite difficult to explain it. So I took some gap. I took a long gap, and explaining it again would be quite difficult. So let's say I have a 3D surface. This 3D surface is defined by f, x, y. So this function over here is defined by f of x, y. And then it's differentiable everywhere. So at a particular point, we can find derivatives. Like, let's say one pointing in the x direction, and one pointing in the y direction. So so this surface is defined by f of x, y, and then we have another thing called the gradient of f. It's just a white one. So gradient of f is partial derivative of f with respect to x in the I direction plus partial derivative of f with respect to y in the j direction. So this vector plus this vector gives the gradient of f. Gradient of f is the partial derivative of f of f in the x direction, this vector, and then this j vector, f, a partial derivative of f in the y direction. The length of this vector is the partial derivative in the y direction, then the length of this vector is the partial derivative in the x direction. So this vector is parallel to the xy plane because there's only I and j, right? So I is like in this direction, j is like in this direction. These two vectors, they're parallel to this plane. So for the entire surface, we can define all of the gradient just in the xy plane. Since f is a function, there won't be like two values for a particular xy. So for every xy input, there will be a unique z output, right? So for every xy input, there will be a unique z output, and we can display the gradient of f in just the xy plane. So for example, this can be displayed over here. And then if we have a gradient over here, like much above, can still be displayed here. And suppose maybe at this point, the gradient is decreasing. If the gradient is decreasing, then it would be negative. So negative in this direction, positive, positive. maybe in that direction. So I can like do this and then this. Wait, I need to check something. Hold on. All right. So where was I going with this? Yeah. This f sometimes he represented with a different function called the vector field function. A vector field function. So a vector field function gives like it's like defined by two equations: p of x y I and then q of x y j. A vector field function. This function just defines the vector field, like this one over here. So f of x y defines some vector field. So here, actually. Well, it's actually the sum of these. So it's actually one vector, but I'm representing them as two. So maybe negative, maybe it would be negative over here. Maybe components would be large over here, and so on. So a vector field, so this gradient of a function is also a vector field. A vector field is called conservative if there's a function that can be represented as its gradient. So if there is some function g and I can write gradient of g, let's say I make this g. G is a conservative vector field if there's a normal 3D function called g of xy where the gradient of g of xy is equal to g. G is a conservative vector field if there is a if it's a gradient of some function, if I can represent it as a gradient of some function. Because some vector field, I can't represent them as a gradient of some function. They're just vector fields, but they are not gradient to any surface. Yeah, and if this thing is possible, if this is possible, then G is called the potential function of the vector field, capital G. So we learned about conservative vector field. And there was a theorem, a fundamental theorem. Yeah. So this over here, this is a vector line gradient. So if f is a conservative vector field, then I can write like this of g times uh and then this. So the gradient of f, and then the fundamental theorem says that I take f at point B minus f point A, that this is equal to this. That's the thing I learned last. Oh, wait. Sorry. Not A and B. F of R, B, R, A. This is the fundamental theorem of line integrals. Fundamental theorem for line integrals. That's the main part, right? Yep. So let's study Green's theorem. So we studied this last time. Let D be an open, simply connected region with a boundary curve C. That is piecewise smooth, simple, closed curve oriented clockwise. Oriented clockwise means the curve is going in a oriented counterclockwise means the curve is going in a counterclockwise direction. Let f p is equal to pq be a vector field with a component function that have continuous partial derivatives on D. Then this integral, the vector line integral, is we can write it like this, which is equal to the area of qx minus py. So the derivative of q with respect to x minus derivative of p with respect to y. Okay. So if we want, let's see. But the thing is, if you go around and come back, wouldn't the thing be zero? Applying Green's theorem over a rectangle. But the thing I don't understand is if you apply this, RA and RB is at the same point. You go around, wouldn't it be zero? FRB minus FRA is zero, right? Simple closed plane curve C to double integrals over region enclosed by C. Let's say example 6.38. Maybe F is not conservative. I think this only works if F is conservative. Example 6.38. So the line integral is x square y dx plus it with y minus 3 dy. Where C is a rectangle with the vertices 1, 1, 4, 1, 4, 5, 1, 5. 1, 1, and 4, 1. 4, 5. 1, 5. Oriented counterclockwise. So we can write this as P dx plus q dy. Q dy. So f is equal to p q. F is equal to x square y minus 3. This is the double integral qx minus py. What is d though? So curve C and then area of D. So the integral is on the region D, right? Qx minus py. Qx 0. Py is x square minus x square minus they said this area, right? 1141. So we should integrate the y aspect first. And then x. X goes from 1 to 4. Y goes from 1 to 5. X square y 5 1 dx. This is 4xy x square dx minus 4. Is this right? Hold on. The integrated x first. 4 cube over 3 minus 1 is 21. And 21 times 4. So it's minus 84, right? So this only works when it's not conservative, right? Otherwise, if it is conservative, then the thing would be 0. Calculate the area enclosed by the ellipse x square over a square plus y square over b square equals 1. Let C denote the ellipse and D be the region enclosed by C. Recall that an ellipse C can be parameterized by x is equal to a cos t, y is equal to b sin t. Calculating the area of t is equivalent to computing double integral. To calculate this integral without Green's theorem, we will need to divide t into two regions. The region above the x-axis and the region below. The area of the ellipse is... So we are doing this with... Shouldn't there be a function inside? Oh no, this function inside is like the third dimension, right? It's what z is. So we just make z is equal to 1, right? So from 0 to this. Okay. Dy 1 minus x squared over a square. Then multiply it with b. Okay, I understand. Then from minus a to a. From minus a to a. From 0 to here. But don't you need to just double this? So you need to only calculate one of them, right? These two integrals are not straightforward to calculate. Instead of trying to calculate them, we use Green's theorem to transform this into a line integral around the boundary C. Consider the vector field minus y over 2, x over 2. Then we have qx and py. Therefore, qx minus py is equal to 1. Now we have this. Okay, and then this is equal to this. They took the half out, minus y plus x. 0 to 2 pi. Then we are left with pi ab. Therefore, the area of the ellipse is pi ab. Use the vector field f is equal to minus y over 2 x over 2 to find the area of any ellipse. The logic of the previous example can be extended to derive a formula for the area for any region T. Let T be any region with a boundary that is simply closed C oriented counterclockwise. If f is this, then qx minus py is equal to 1. Therefore, by the same logic as in example 6.40, area of T is this. Flux form of Green's theorem. The circulation form of Green's theorem relates a double integral over region D to line integral, where C is the boundary of D. The flux form of Green's theorem relates a double integral over region D to the flux across boundary C. The flux of a fluid across a curve can be difficult to calculate using the flux line integral. This form of Green's theorem allows us to translate a difficult flux integral into a double integral that is often easier to calculate. So the flux F times NDS is Px plus Qy dA. Because this form of Green's theorem contains unit normal vector, it is sometimes referred to as normal form of Green's theorem. By circulation form of Green's theorem, we have this. Then we have Px plus Qy. So we have example 6.41. You want to calculate the vector field is f of x, y. Is this the vector field? X, y. So p is equal to x, q is equal to y. P of x is 1, q of y is 1. Let C be a circle of radius r centered at the origin. Let F be this. Calculate the flux across C. X square plus y square is r square. The flux across C, which is F dot n ds, is equal to area of this which is equal to this. This gives 2, right? But here's the thing, how do we separate the x and y? So x goes from minus r to r, minus r, r, and then y goes from 0 to r, y goes from 0 to r, dy, dx. And then we need the double of this, times it by 2, because we need the entire area. Oh no, wait, it's just pi r square. I don't need this integral. So 2 pi r square. Okay, so the vector field is defined like this. And then px is 2x, qy is 1. Therefore, we have 2x plus 1. And then we have this area. Why is there a minus? Green's theorem applies only to simple closed curve oriented counterclockwise. But we can still apply the theorem because this is my... Okay, so if it's clockwise, we have to multiply it by negative, right? Notice that the top edge of the triangle is the line y is equal to minus 3x plus 3. Therefore, in the iterated double integral, the y value runs from 0 to y is equal to minus 3 plus 3. Then we get minus 5 over 2. Recall that if vector field f is conservative, then f does no work around closed curve. That is, the circulation of f around a closed curve is 0. In fact, if the domain of f is simply connected, then f is conservative if and only if the circulation of f around the closed curve is 0. If we replace circulation of F with flux of F, then we get a definition of source-free vector field. The following statements are all equivalent ways of defining a source-free vector field on a simply connected domain. The flux across any closed curve C is 0. So even the flux is 0. Px plus qy is 0. C1 and C2 are curves in the domain of F with the same starting point and F points. Then this is equal to this. In other words, flux is independent of path. There is a stream function g of xy for F. A stream function is a function g such that p is equal to g of y and q is equal to minus g of x. Geometrically, FAB is tangential to the level curve of t at AB. Since the gradient of g is perpendicular to the level curve of g, hold on, the gradient of g is perpendicular to the level curve of g at AB. Same function g has the property FAB times gradient of g is equal to 0 for any point AB in the domain of g. Vector fields that are both conservative and source-free are important vector fields. One important feature of conservative and source-free vector fields on a simply connected domain is that any potential function f of such a field satisfies the Laplace's equation fxx plus fyy is equal to 0. Laplace's equation is foundational in the field of partial differential equations because it models such phenomena as gravitational and magnetic potentials in space and the velocity potential of an ideal fluid. A function that satisfies Laplace's equation is called a harmonic function. Therefore, any potential function of a conservative and source-free vector field is harmonic. To see that any potential function of a conservative and source-free vector field in a simply connected domain is harmonic, let f be a potential function of the vector field capital F, then fx is p, fx is, wait, what? I think fy is q. I think that's what they meant. Because gradient of f is equal to capital F, therefore fxs is equal to px and fyy is equal to qy. Since f is source free, then fxx plus fyy is equal to px plus qy is equal to 0, and we have that f is harmonic. Verify that the field is both conservative and source free. Find a potential function for f and verify that the potential function is harmonic. So this is equal to sine y cos y. Hold on. So we have sine y, cos y. So they want to say, verify that veil is both conservative and source free. So P is equal to this. Q is equal to this. And then Px is equal to e to the power of x u y is wait, sine y is a constant. It's treated as a constant, right? And over here, ex is treated as a constant, and then minus si- derivative of cos is minus sine. And if yeah, and then b with it, we need to show that the cross partial derivative property, in order to show that it's conservative, b with respect to y is e to the power of x is constant. Derivative of sine is cos. Uh, e to the power of x cos y. P is equal to qx. Therefore, conservative. So that means there exists a function f. There exists a potential function f. And then p x plus q y is equal to 0. Therefore, source free. And now we need to find the potential function f. F is equal to e of x sine y. We derivate this with respect to x, we get e of x sine y, which matches this. Derivate this with respect to y, we get e of x cos y, which matches this. Now we need to show that it's harmonic. If this is harmonic, how do we show this is? Px qy is 0. So therefore source free and f is harmonic, right? This shows it's source free and that the potential function is harmonic. And potential func is harmonic. Green's theorem on general regions. Before discussing extensions of Green's theorem, we need to go over some terminology regarding the boundary of a region. Let D be a region and let C be a component of the boundary of D. We say that C is positively oriented if, as we walk along C in the direction of the orientation, region G is always on our left. Therefore, the counterclockwise orientation of the boundary of a disk is positive orientation, for example. Curve C is negatively oriented if, as we walk along C in the direction of the orientation, region D is always on our right. Clockwise orientation of the boundary of a disk is a negative orientation, for example. Let D be a region with finitely many holes. Denote the boundary D by delta D. To extend Green's theorem so that it can handle D, we divide region D into two regions, D1 and D2, such a way that D is D1 union D2, and neither D1 and D2 has any holes. Assume the boundary of D is oriented as in the figure, with inner holes given in negative orientation and the outer boundary given a positive orientation. Boundary of each simply connected region D1 and D2 is positively oriented. Where F is a vector field defined on D, then Green's theorem says that this is equal to this, is equal to this, so no changes. Same logic implies that the flux form of Green's theorem can be extended to a region with finitely many holes. So qx minus py. Then we have x squared plus y squared. We are left with 15 over 4. Yeah, I think that was the last section they talked about. I think the last part was a little confusing, but I would need more practice. Anyways, I will end the stream here then. And yeah, I will see you guys next time. Bye.